So let's take a look at how these different concepts of bonding in molecules apply to a very specific case, the case of ethylene, C2H4. If you first approach the structure of C2H4 from a Lewis dot perspective, you can apply the octet rule, and what that quickly tells you is that you would put a pair of electrons between carbon and each of the hydrogens, leaving a total of 4 electrons in between 2 centrally located carbon atoms. This corresponds to a picture, of course, of a carbon-carbon double bond with single bonds to 4 hydrogens around the periphery. That picture for electron distribution is not wrong, but it doesn't tell you anything about the 3-dimensional shape of the molecule. It works very well when drawn on a sheet of paper, but not so much when held up in your hand. For that, you can get some initial insight by applying valence shell electron pair repulsion. That tells you that the carbon atoms are trigonal planar with 120-degree bond angles, but it only tells you about the planarity at each of the carbons. In fact, it doesn't tell you about how the plane associated with one of those carbon atoms is oriented relative to the plane associated with the other carbon atoms. They could be coplanar, they could be orthogonal, they could be somewhere in between. To understand the planarity of ethylene, you need to move to the model of hybridization, right, which describes the pi bonding in the double bond as corresponding to the overlap of leftover atomic p orbitals on each of the 2 carbon atoms. Okay? That in turn leads to full planarity for all 6 atoms in this molecule, for all 6 nuclei. Okay? And so that gives you the shape, and to get there you need to go all the way up to hybridization theory. But if you start now expanding to more complicated molecular structures, and in particular let's consider polyacetylene, which has it's a polymer which has the repeating structure shown here, just alternating carbon-carbon double and single bonds. I haven't drawn the carbons at the intersections of these lines simply for reasons of trying to keep the picture clear, but that's the molecule. You can imagine it as being a series of ethylenes in which we just plucked off a couple of hydrogens and stuck the intervening carbons together. Okay. One of the neat things about polyacetylene is that it's got this conjugated pi structure that you learned about in some of the later sections in this unit. And that conjugation is something that can't be explained by hybridization, valence shell electron pair repulsion, certainly not by Lewis structures themselves. It really requires a molecular orbital description in order to get the conjugation, which has important implications, as you'll see in some of the supplemental materials in this section, for the electronic properties of polyacetylene. So the take-home message here is to realize that at the end of the day, all of these, be it Lewis dot structures, molecular orbital theory, or something in between, are just models. And you need to be aware of the limits of each, and also the experimental observations that make each of them necessary in certain cases.